The last part of chapter 27 looks at separable differential equations, another way to solve a differential equation. And this is for the specific case where you have a derivative equal to essentially something that can be separated out into all of the x's on one side and all of the y's on the other. It's usually consisting of f of x divided by g of y, or f of x times g of y. So we can just simply multiply or divide to get our variables separated. So what we can do is, in this case, we can multiply both sides by g of y, this function of y, and then here we can integrate both sides with respect to x. And what happens is the dx's on the left cancel out. So we're taking the integral of the y's with respect to y on the left hand side, and the integral of the x's with respect to x on the right hand side. So here is an example of a separable differential equation. And we're going to find the general solution. We want to find out what does y equal. But the problem is the derivative involves y. So what we're going to do is we're going to separate this. Essentially this problem becomes, I can divide both sides by a minus y. K is a constant. This is what I've got. This is equal to negative natural log of a minus y equals k times x plus c. We only need a plus c on one side. Now, I'm going to move this negative to the other side. I'm going to get the natural log by itself, and then we're going to change this to exponential form. So a minus y equals e to the negative kx plus c. I'm still adding some constant. I move the negative the other side, but the constant still stays just a constant. And then this thing right here, and remember a is a constant, it's some unknown constant value. E to the kx plus c, that's the same thing as e to the negative kx times e to the c. Well, e to some constant is still just a constant. So I'm going to call it this new constant. Call it b. And then I need to move the a to the other side. So negative y, well, I'm still adding a constant. It may be negative, maybe positive, I don't know. I'm not given any information about it. And then I have to divide both sides by negative 1, but really, I'm dividing a constant and a constant by a negative. All it's going to do is change the sign of those numbers, and I don't know those numbers, so I'm okay. This is my general solution. Now, we want to solve this for v. Again, this derivative of v with respect to h is equal to a function of v. I want to separate this into two parts. The integral of v to the negative 1/2 dv equals the integral of k dh. So I have this. This right here, if I were to get v by itself, would be considered the general solution. But I'm given some information here about some specifics. I'm given some conditions up here that the volume when h is 9 is equal to 1, and the volume when h is 13 is equal to 4. And I guess I'm assuming that v is standing for volume. It doesn't have to, I guess. But I can use this down here to find a system of equations that will allow me to find k and c. So 2 times v to the 1/2, 2 times 9 to the 1/2, that's going to be equal to 6. Because 9 to the 1/2, 1 to the 1/2 is 1 times 2 is 2. Equals h times k, so 9k plus c. And then I can use the second value here. 4 to the 1/2 is 2 times 2 is 4 equals 13k plus c. And I'm just going to subtract these two equations. Negative 2 equals negative 4k. The c's cancel out in this case. Therefore, k has to be 1/2. And doing some substitution, c is equal to negative 5/2. And this is going to allow me to get a specific solution. 2v to the 1/2 equals 1/2 h minus 5/2. And I can divide both sides by 2, leaving me with h minus 5 over 4, and square both sides. Squared is equal to v. There is my specific equation given these known conditions. So in this problem we have some curve, f of x. It has a y-intercept of 3. The tangent to this curve at x comma y has an x-intercept of x plus 2. I'm going to make a quick sketch here. I have some curve that crosses at 3, and there's some point here, x comma y, that when I draw the tangent to the curve, here's x, this point down here is x plus 2 comma 0. This is the information that we're given. So dy dx, change of y with respect to x, is equal to 0 minus y over x plus 2 minus x. What I'm doing is I'm finding the slope of this line, and I'm using a slope triangle right there. And it's just rise over run. 0 minus y, x plus 2 minus x. And I can clean this up just a bit. dy dx is equal to negative y over 2. And this is a separable differential equation again. I get the integral of dy over y, divide both sides by y, equals negative 1/2 times the integral of dx. So the natural log of y is equal to negative 1/2 x plus c So then I know that y is equal to a times e to the negative 1/2 x. And since I know that f of 0 is equal to 3, I can figure out what a is. Remember, the reason I get a here is because e to the c is just some constant. So plugging in for this, 3 equals a times e to the 0, so a has to equal 3. So my specific solution for this differential equation is that y equals 3e to the negative 1/2 x. Or we could say 3e to the negative x over 2. This problem deals in bacteria, and I'm going to say that n is the number of bacteria, and t is equal to the number of hours that have passed. And it says that the number of bacteria is proportional to the number present. So what that tells me is that, the increase of the number of bacteria, so dn dt, is proportional, that's what this symbol would mean, is proportional to the number present. So it's proportional to n. In other words, dn dt is equal to a constant times n. And here's a separable differential equation. So the natural log of n is equal to kt plus c, or n equals ae to the kt. Now, the textbook works through this example slightly different, but I am going to get the same answer here. We know that at t equals 0, the amount present is equal to the initial amount. So let's call that n sub 0, initial amount. So we now can write n equals n sub 0 e to the kt. And we're also told that the number increases by 10% in 1 hour. So if the initial amount is n sub 0, that means that after 1 hour there will be 1.1 n sub 0 present. So 1.1 equals e to the k. K is equal to the natural log of 1.1. So what I'm trying to do is I'm trying to come up with the best equation that I can for n. And what I figured out is that n needs to be whatever the initial amount is times e to the natural log of 1.1 times t. And what I can do here is I can group this and write n equals the initial amount, e to the natural log of 1 is just 1.1 to the t. Now I'm going to use the rest of the information in this problem. It says, what percentage increase occurs after 5 hours? And what this should say is after 5 more hours, which means that t equals 6 for this last part of the problem. So n is equal to n sub 0 times 1.1 to the 6th. One point one to the 6 is 1.7716. So after 6 hours, we are 1.7716 times the initial amount, which means our percent increase is 77.16%. And the last example that we have to look at here is a falling raindrop that has an acceleration of 9.8 minus v divided by 3 meters per second squared. We want to show that the raindrop's velocity is given by this equation, and then we're going to look at what the terminal velocity of this raindrop is. That is the fastest that it will ever go. So if we know this is the acceleration, we're trying to get to velocity. That means that dv dt is equal to this. And I can write this so that it's one fraction. And this one fraction would be 29.4 minus v divided by 3. I want to do this because my derivative of v involves v. So I need to separate my variables. And I can't do that if it's addition and subtraction, only if it's multiplication and division. So what I'm left with is dv over v minus 29.4. Now you might ask, how'd I do that? Well, I'm going to make this side be negative 1/3. Pull a negative out of here, and I did this. And you might ask, well, why do you want to do that? The reason is, if I don't, I'm going to have to do a basic u substitution when I take this integral. Here I can just say that this is the natural log of v minus 29.4. And here, this is another exponential problem. V minus 29.4 equals AE to the negative t over 3. And we're actually given an initial condition in this problem, although we may not recognize it. When t equals 0, the velocity is equal to 0. It hasn't started falling yet. There is no speed. And doing that, we find that our constant a needs to be negative 29.4. So our velocity is equal to negative 29.4 minus or it would be 29.4 minus 29.4 e to the negative t over 3. And doing some simple factoring, we get to where we were trying to get to. Now, I mentioned that we were going to look at the terminal velocity for this. In other words, what happens to this velocity as the time gets big? And what happens is this e to the negative big number becomes 1. And 1 minus, or it becomes 0. And 1 minus 0 is just 1, so this terminal velocity of our raindrop is 29.4 meters per second. So I've given you several different examples of how we can use separable differential equations, and hopefully these examples will help you work through these problems in your assignment.